In this video, we begin section 3.2.6, Gauss-Jordan Elimination. We've already talked about Gaussian elimination. Now we're going to talk about Gauss-Jordan elimination, which is another method for solving linear systems. What is the method? Well, given a system of linear equations, we can solve it as follows. Step 1 is to write the augmented matrix of the system of linear equations. This is the same as the first step for Gaussian elimination. Step 2 is to use elementary row operations to reduce the augmented matrix to RREF, to reduced row echelon form. In Gaussian elimination, we reduce the augmented matrix to row echelon form. In Gauss-Jordan elimination, we reduce the augmented matrix to reduced row echelon form. Step 3 is then to write the new system of linear equations corresponding to the augmented matrix in RREF. And step 4 is to solve the new system using back substitution. So let's look at example 3.2.14. We want to solve the following linear system using Gauss-Jordan elimination. We start with step 1, which is to write the augmented matrix of the system of linear equations. So step 1 is to write the augmented matrix, which is 1, minus 1, 3, 8, 3, minus 1, 9, 20, 2, minus 4, 5, 19. This is the augmented matrix of the linear system. Step 2 is to reduce the augmented matrix to reduced row echelon form. We want to perform elementary row operations, and we can start by reducing the augmented matrix to row echelon form. That's something we're used to doing. And so we know that at least these 3 entries in the bottom left corner of the augmented matrix must be 0 for a matrix of this size. And so we can start with the first column. In order to get a 0 in the position of that 3, we can use the row operation, row 2 minus 3, row 1. And in order to get a 0 in the position of that 2 in the first column, we can use the elementary row operation, row 3 minus 2, row 1. So the first row stays the same, 1 minus 1, 3, 8. The second row becomes 3 minus 3, that's 0, minus 1 plus 3, that's 2, 9 minus 9, that's 0, 20 minus 24, that's minus 4. And the third row becomes 2 minus 2, that's 0, minus 4 plus 2, that's minus 2, 5 minus 6, that's minus 1, 19 minus 16, that is 3. That's the new third row. Now this matrix is not yet in row echelon form, and so we need to perform more elementary row operations. We would like to have a 0 in the position of this minus 2, and so we can use the elementary row operation row 3 plus row 2 to make that happen. So we're going to get 1 minus 1, 3, 8 in the first row. That first row hasn't changed. The second row does not change either, 0, 2, 0, minus 4. And then in the third row, we have 0 plus 0, which is 0, minus 2 plus 2, that is 0, minus 1 plus 0, that's minus 1, and 3 plus minus 4, that is minus 1 as well. This augmented matrix is now in row echelon form, but we want to reduce it all the way to reduced row echelon form. It is not yet in reduced row echelon form. Notice that the leading entries are not all leading ones. The leading entry in the second row is a 2, not a 1. With the help of the elementary row operation 1/2 row 2, we'll be able to replace that 2 with the leading 1. And in the same way, in the third row, the leading entry is currently a minus 1. We want a leading 1 there. So if we use the elementary row operation minus row 3, we'll get a 1 there as well. So let's do those two elementary row operations. So we have 1 minus 1, 3, 8. The first row isn't changing. The second row becomes 0, 1, 0, minus 2. And the third row becomes 0, 0, 1, 1. Now, is this matrix in reduced row echelon form? Not yet. We need that each column containing a leading 1 has only zeros above and below the leading 1. We actually need all of these entries to be 0. If all of those entries are 0, then we will have that each column containing a leading 1 has only zeros above and below the leading 1. Let's start with that 3. Which elementary row operation can we use so that we have a 0 in the position of that 3 in the next step? We want to change row 1, and we can use the third entry of the third row in order to get a 0 in the position of that 3. We can use the elementary row operation row 1 minus 3 row 3. So the first row is changing. We have 1 minus 3 times 0, that's 1. Then we have minus 1 minus 3 times 0, that is minus 1. Then we have 3 minus 3 times 1, that is 0, the 0 we were looking for. And then 8 minus 3 times 1, that is 5. And the other two rows stay the same. So 0, 1, 0, minus 2, 0, 0, 1, 1. This augmented matrix is not yet in reduced row echelon form. The problem is that in the second column, we do not have that there are only zeros above and below the leading 1 that we have there. We have a minus 1. If this minus 1 is replaced by a 0, then the augmented matrix will be in reduced row echelon form. So which elementary row operation can we use here? We want to change row 1. If we add row 2 to row 1, we will get a 0 in that position. So the first row becomes 1 plus 0, which is 1, minus 1 plus 1, that is 0. 0 plus 0 is 0. And then we have 5 minus 2, that is 3. And the second row and the third row, they both stay the same. This matrix is now in reduced row echelon form. And so now I move on to step 3. Step 3 of Gauss-Jordan elimination is to write the system of linear equations corresponding to the augmented matrix in reduced row echelon form. So my corresponding system that I get in step 3 is going to be x equals 3, y equals minus 2, and z equals 1. This is the corresponding linear system. Now notice that I have already found x, y, and z. X is equal to 3, y is equal to minus 2, and z is equal to 1. Step 4 is the back substitution step. And there's actually no need for back substitution. Because I've already found x, y, and z. So I can write the solution. The solution to the system is x, y, z equals 3 minus 2, 1. By reducing the augmented matrix all the way to reduced row echelon form, we eliminated the need for the back substitution step.